Thank you all for coming. And I'm really glad to be here and very honored to be the last speaker of today. And I would like to use this to thank Nalini and Thibault for putting this event together. Let's just give them an applause for this. So today I'm going to tell you a recent work I did with Yuhao Xue, who is a postdoc at the IHES, who is sitting there. And the key message of today is to show you we can actually use probability to prove some results about geometry. So it's not exactly about random geometry, but it's still geometry and probability. So I will introduce what these guys are, but Brownian loop measure, determinants, and Laplacian. But let me start with the Riemann surface. First, a Riemannian surface that will be considered in this talk is a surface equipped with a smooth Riemannian metric and without boundary. So on the right, you see a picture of a surface which seems to have a boundary, but I just mean that I don't include the boundary as part of the surface. Apart from that, I don't assume anything else. So the surface can have some punctures, can remove some points from it. Does not need to be geometrically finite. It can have infinite genus. It can have infinitely many punctures. And the uniformization theorem tells you that for any such Riemannian surface, there exists a metric of the form some positive function times the metric, such that under this new metric, this surface would have constant curvature either 1, 0, or -1, and is complete. So in the case, there's a classification. If you have a constant curvature 1, then there's only one choice. This is the sphere. Curvature 0, it's a flat surface. It can only be the complex plane, or the complex plane removed by 1 point, or torus, which is just the quotient of the complex plane by a lattice. And anything else will be hyperbolic with curvature -1. And in particular, in this case, the hyperbolic metric is unique. And by Riemann surface, I just mean the surface equipped with complex structure. And in this case, it also can be viewed as a conformal class of the metrics. So all the metrics in the same conformal class. So here, you have an original metric here, and this is a new metric, which is conformal to the original metric because the metric is just obtained by multiplying the metric at pointwisely by some positive number. That in particular doesn't change the angles of between two vectors. So very simple examples of a hyperbolic surface either is, for instance, the upper half plane. I really want to emphasize that we are looking at complete metric because if you take the flat metric, just Euclidean metric is also constant curvature, but it's not complete. You can have a sequence going to the boundary with the limit to the is on the boundary, but the boundary is not part of my surface. And so the metric we're really looking at is this hyperbolic metric. The other simple example is this hyperbolic annulus. So it is obtained by taking this upper half plane and mod out the scaling. One map, like it would form Z to some scaling of a scaling map. And here, under these arcs, this is a fundamental domain, and where this orange curve is identified with this orange curve. These are the geodesics in the hyperbolic plane. They're identified, and you get this surface. And here, this left band, here, this lines becomes this circle, this line becomes that circle, and there's one geodesic which is homotopic to this, it's homotopically equivalent to the annulus. This is given by this vertical line. So this is this blue line here. And I really need to mention, say this again. This is a hyperbolic annulus. So if you draw this in the complex plane, it is you can draw it on the complex plane, but you really need to think about this boundary. These two black circles, they're infinitely far from the surface. That's why it's a hyperbolic annulus that's complete. And there's only one conformal invariant about this annulus, that's called the modulus, or if you draw in the complex plane, one radius is 1, and the other side, the radius is exponential minus r. And there's a relation between this r with the length of this geodesic. It's really computable, and in this case, it is 2 pi squared over r. So just to say that there's the moduli space of annulus, there's this one parameter. You can either parameterize by this r, or you can also parameterize by the length of the unique simple closed geodesic, which is a function of r. So actually, these will be the 2 examples that are most important to this talk. For other complete hyperbolic surface, they're just obtained as a quotient of the hyperbolic plane modulo a discrete subgroup of the isometries of the upper half plane. So these isometries, they're of the form of this fractal linear transformation, usually parameterized by this PSL2R group. And all the elements here in this discrete group shouldn't have an internal fixed point. And then you get the honest covering of the surface by the hyperbolic upper half plane. And here is this one example. I draw the fundamental domain of this surface. Here you see if my fundamental domain contains some part of the real line, this becomes this part of the surface. It's called a funnel. And it can also have a single point removed. Like this will correspond to some cusp. You see from the fundamental domain, you can be like 2 geodesics meeting at the same point on the boundary. Yeah, so I still, again, have to emphasize again, this is either the cusp and this funnel under the hyperbolic metric, they're infinitely far seen from any point of the surface. For a hyperbolic surface, there is some nice feature. For instance, for each free homotopy class of closed curves, there exists a unique geodesic in this free homotopy class. So by free homotopy, it just means like these 2 curves, this orange curve and this red curve, they are freely homotopic if you can modify one continuously to the other. And for each class, there's only one geodesic. You can imagine you start with an arbitrary curve and you pull it tight, and there's only one limit possible. And this is the shortest curve, is the hyperbolic geodesic in the class. So this is not true if your homotopy class is trivial or it can contract to a cusp. In this case, if it's not trivial or contracting to a cusp, then we call this free homotopy class essential. So apart from these 2 cases, there exists a hyperbolic geodesic. The other case is that if I have a flat torus, the torus which comes with its flat metric, so the metric on C given by the Euclidean metric, in this case the geodesic is not unique because a geodesic can, if you draw a straight line between these 2 elements in the lattice, it projects down to a geodesic on the torus, but you can also glide, you can slide this geodesic by a translation. It gives you another geodesic with the same length. But however, we can still talk about their length. So the first one, since the hyperbolic geodesic is unique, I just define the length of the homotopy class as the one of the geodesic. And in the second case, all the geodesics are related by sliding around the torus. They have the same length, so the length is still well defined. And all the other case, meaning the sphere minus 1 point, sphere minus 2 point, you can see there's no curve that's not homotopic to a point. And so we only care about these 2 cases, complete hyperbolic or a flat torus. Another notion is about the multiplicity of a geodesic. So if I have a geodesic So a curve being a geodesic is a local property. I can very well round my geodesic by wrapping around some other geodesic several times. So m is the number of times that is wrapped around the shortest geodesic. And here in this example, this is 2. The multiplicity is 2. And if the multiplicity is 1, we call this geodesic primitive. And being a primitive curve doesn't mean it's simple. And for instance, this red curve is still primitive, but it has a self-intersection. Okay, these are the basic terminology, and we can state our result. Okay, let X be a complete hyperbolic surface with no condition. I take a set P is a closed countable subset of X. X prime is the surface obtained by removing from X this closed set P. I still get the Riemann surface. And this is a Riemann surface, which is not the sphere. It's not the sphere minus 1 point. It's not the sphere minus 2 points. It's not the torus. So it has a complete hyperbolic metric. And I will just use this as this complete hyperbolic metric. And now the points where it has been removed, they become cusps. Since the metric is complete, they're really cusps. They are points that are very pointed. And here, if I put a lot of points, then we'll get a lot of cusps, and this surface really becomes very spiky. I don't assume how many points there are, apart from they're countable. They can be finite as well. And also don't assume where they are. You can put arbitrary place. The result is as follows. If I start with a closed geodesic gamma on the left, I have the following identity. Here on the left, everything expressed in terms of the hyperbolic metric of X, 1 over the multiplicity of gamma, multiplied by 1 over exponential length of gamma minus 1. On the right-hand side is a sum over the geodesics of X prime, summing over all the geodesics that would have been homotopic to gamma in the previous surface. For instance, here I draw a picture of one example of a gamma prime, which goes around the same handle, but also wrap around the cusp. So if you fill in this cusp, you will get the curve that will be freely homotopic to gamma. On the right-hand side, there's always infinite sum, but countable. For instance, you can go around this cusp several times. You can go inside another handle and wrap around a cusp and undo the handle and come back. It also would be another example of a curve appearing in the sum. And on the right-hand side, it's the exact same formula, but everything expressed in terms of the metric of X prime. And we claim that this is an identity, which is true for any closed geodesic gamma. If we have a torus, then what you do is to replace the left-hand side by area of the torus with respect to the flat metric divided by pi length squared. On the right-hand side, if I remove at least 1 point, then it's a hyperbolic surface. So the expression, again, is using hyperbolic metric. Okay. Okay, it's dying.
Sorry, may I ask?
Yeah.
Maybe I missed what you said in the beginning. In your first identity,
yeah.
on the left-hand side, everything has to do with hyperbolic metric on X.
Yes.
And what you do is that X prime, you remove some points.
Yeah.
You recompute the hyperbolic metric for that?
Yeah, but on the right, that's on the right.
Okay, so you change the metric?
Yeah, you change the metric and do the sum. Okay, yeah. Yeah, you can do that. You allow that. Okay, now it's back. Yeah, other questions about the statement? Okay, maybe one comment. This is just the same formula. If gamma is primitive, meaning m equals 1, It simplifies, this goes 1. And this is also 1 because the multiplicity of the curve gamma prime should divide the multiplicity of gamma. It gets simpler. And I think I should also remind you about the famous McShane identity, if you've ever seen this. So this is the simplest version of McShane's identity. It's about 1's puncture torus. Also, he doesn't take any 1's puncture torus. He takes the sum over all oriented simple closed geodesic and summing over 1 over exponential the length plus 1, and it always equal to 1. So in our identity here, the sum there always contains non-simple curve because you have to allow them to go around punctures. But here, there's only about those simple closed geodesic. Those doesn't intersect itself. And in particular, if we apply that in our case, we can also just add 1 point. We would have an identity of area divided by length squared equal to sum over those geodesic, but with 1 over this minus 1. Yeah, so it looks very much like what McShane is doing. So the proof of our result with McShane's identity has nothing to do with each other, but I still find this a very beautiful idea, so I'm just doing this quickly. So the idea of McShane is the following. You first take a horocycle around this cusp. So by horocycle, I just mean that if you look at this in the universal cover and the horocycle, let's say if the cusp corresponds to a point at infinity, the horocycle is a line which is parallel to the x-axis. And you pick 1 point uniformly at random. So this is a probability measure on this line. And you start from this point an orthogonal geodesic. And you wait until it first time hits itself, or it goes back to the horocycle. And actually, there's another scenario that can happen is that this geodesic is going to wrap around and getting closer and closer to some closed geodesic. But this thing happens with probability 0. Let's just look at these two cases. In these two cases, I would just assign a simple closed geodesic to each scenario. In this case, I will assign the curve that's homotopic to the first loop, which appeared here. And in this case, I look at the complement. So now if I cut open the horocycle, I cut open this geodesic, I get some annulus, and annulus contains 1 geodesic. So each gamma can come from either scenario. But so you compute these two cases together, the probability of seeing a particular curve, gamma, is exactly 1 over exponential the length plus 1, and therefore they have to sum to 1 because that's a probability measure. Miyazaki has developed further this idea by decomposing geodesic, this orthogonal geodesic coming from some surface with geodesic boundary. And she generalized this McShane's identity, and that has led to a computation of the Weil-Petersen volume of moduli spaces. And also there are other identities about the length spectra of surfaces, which is not the exhaustive list, but I just pick a few representative ones. For instance, Basma-Zhao has a work which relates the length of geodesic boundary of a hyperbolic surface to the length of orthogeodesics. These are geodesics that are orthogonal to the boundaries. And also Bridgman had works on orthogeodesics, by decomposing the unit tangent bundle of the hyperbolic surface and depending how the geodesic behaves according to the starting point. And you can also obtain identities about orthogeodesics. And there are a lot of other generalization, modifications, and which I'm not giving the full list. But all these identities, they're really about the length of one surface. And in our case, we are considering the length of two different surfaces. Let me just rewrite this identity. So far nothing is probabilistic, but we're going to use probability to prove this. There are just two main ideas. We use Brownian motion on the Riemannian surface with some metric. Like here is a hyperbolic metric. And in 2 dimensions, Brownian motion has a remarkable property for being conformally invariant. And the other property of a 2-dimensional Brownian motion is that the probability of a Brownian motion, apart from if it starts from the point, if it doesn't start from the point, the probability of the Brownian motion hitting a particular point is 0. And the probability of Brownian motion hitting a countable set is also 0. And we're just going to combine these things together to get this. And more precisely, the Brownian motion that we're going to use is the so-called Brownian loop measure. And it was first, so Brownian loop measure is an infinite measure, but sigma finite, finite measure on Brownian type loops on a Riemannian surface. I will come back to the more precise definition here, just giving you a background where you see them. And they were really made in the way that I'm going to introduce. It was introduced by Greg Lola and Van Leen Werner in the study of Schramm-Lövner evolution on the sphere. So it was done originally on the sphere, but the generalization to the Riemannian surfaces, that's almost immediate. And this Brownian loop measure has been used also to describe some stress energy tensor of SLE loop measure. You can track back to the early work about the conformal restriction property of SLEs. Don't worry if you don't know exactly what that means, but these are the key tools to describe the laws of SLE. Like for instance, if you throw a Poisson point process of a Brownian loop measure with certain intensity, then the outer boundary of the clusters, this gives you an infinite collection of simple curves, and they're called the CLE loop measure. And also, the total mass of Brownian loop measure on the surface, which I told you is infinite, but there is a way to renormalize it such that it gives you the log determinant of the Laplacian. And the log determinant Laplacian is important to be in physics, also being the partition function of the Gaussian free field, appear as a conformal anomaly of conformal field theory. And this relation between total mass and the determinant Laplacian is observed by Yves Lejean here, Julien Dubeda, and also made precise in ways by these people. So let me just do it gently. First, I tell you what is Brownian motion on a Riemannian surface. Okay, if I have a metric on the surface, I can define what's this Laplace-Beltrami operator. Here, I don't need to assume the metric to be complete. If the Brownian motion has a chance to hit the boundary in finite time, then I just kill this Brownian motion. And in R2, it's very concrete. Okay, in R2, if my metric is Euclidean metric multiplied by some smooth function, then the Laplacian is just exponential minus this 2 sigma times the usual Laplacian. And this is not true for other dimension. It's just 2 dimension. This is true. And a Brownian motion generated by such a Laplace-Beltrami operator is just a time change of a standard Brownian motion. I won't write down exactly how the time change works, but if I just care about this trajectory, which is conformally, if I kill my Brownian motion when it hits the boundary, in the Euclidean plane, that will do something like we stop somewhere on the real line. The trajectory won't be different if I run my Brownian motion in the hyperbolic plane. It just takes an infinite amount of time for the Brownian motion to reach its boundary. So if you want, if I take a picture of, let it give the exposure to infinite time. So the picture I would obtain is exactly the same if it's coming from a Euclidean plane or a hyperbolic plane. And Brownian motion also has a close link to the heat kernel. So PTZW, so of course this depends on the time, it depends on the starting point, the end point, and also the metric. It's not written, but it's always the metric underlying the heat kernel. The heat kernel gives you the density of the Brownian motion starting from Z at W, if you run by time t. So of course, when I say the Brownian motion is conformally invariant, the heat kernel is not conformally invariant. Everything that would involve the time, it won't be conformally invariant. Okay. So now, if we know how to do the Brownian motion on the hyperbolic plane, I can do the Brownian motion on the hyperbolic surface. If I start the point, Brownian motion point on the surface, I just lift it to the universal cover and run my Brownian motion there and project it down. And that's my Brownian motion on the hyperbolic surface. Okay. Yeah, so if it's a complete hyperbolic surface, then the Brownian motion will run forever and never hit the boundary. Okay, now this is probably the slides where it was most definition. So let's assume that my metric is starting with any smooth metric. I look at this measure, subprobability measure on the Brownian path on the surface starting from the point x and run for time t and killed at its boundary. If it's the complete hyperbolic metric, it's never killed. So this will be a probability measure. It's a probability measure on the path. So it remembers where it goes, how it goes through this point. So it's a measure on the trajectory. And now I define the next measure. So this is WT x to y. Y is another point on the surface. So this is a family of measure indexed by x and y, such that this is the disintegration of this first metric with respect to the endpoint, in the sense that this is a measure on the path going from x to y, such that if I integrate it with respect to the endpoints measure, the volume form of the endpoint, which depends on the metric, I get this new metric, new measure. We get this measure, which is the one that I started with. Concretely, if you want to do this, it's just its total mass is the heat kernel. And if you divide it by the heat kernel, you get probability measure, and that is the Brownian bridge on the surface. Okay, now this is not anymore a probability measure because the heat kernel, it just depends on what the heat kernel is. The Brownian loop measure is supposed to average over all the time and all the starting point. But with time, I put the weight 1 over t, and I take the integral over all the points from x to x. So now I ask the starting point and end point to be the same, so I get the measure on loops. And why I divide by 1 over t in some way is you can think this as a bigger loop. There are much larger chance to sample a big loop because the same loop can be obtained by starting from a different point. So when I divide it by t, it's kind of penalizing big loop, but also promoting the small loops. So this is an infinite measure on loops. And the remarkable property about this is probably this one, the conformal invariance. So if I look at the Brownian loop measure defined with the metric g and the Brownian loop measure defined with exponential 2 sigma g, upon forgetting its parameterization and forgetting its starting point, then you get two infinite measures that are the same. And that really thanks to this factor 1 over t in front of it. And another property is this restriction. You have a subsurface, then the loop measure will just be the one which restricted to the smaller surface. This is coming for free because I define my Brownian motion by killing it when it hits the boundary. So really the second property is really the remarkable thing. So also this is a measure. So the good thing about thinking about measures is that it really contains a lot of information. You can ask what is the chance, what is the measure of loops that touches two sets. You give all the information about that. And of course, their total mass are infinity, but as a measure itself, it contains a lot of information. And well, okay, let's try to explore this conformal invariance. I said everything that would depend on time parameterization, it won't be conformal invariant, but things like loops that are in which homotopy class. This is something which doesn't depend on the time parameterization. Everything topological, this will be conformal invariant. And also, we do expect the total mass of Brownian loop inside one homotopy class to be finite. First of all, this quantity, why this is an infinite measure? Because there are infinity coming from t being small and also t being large. So when t is small, the loops are very small. It's very unlikely for a small loop to go doing something non-trivial in the homotopy class. But also, if your t is large, so these loops tend to wrap around each handle in a way like a random walk. So it's going to infinity. So if I fix the homotopy class, this number is finite, and it's actually also computed by Eve about this number in the case of a closed surface. But what we try to do is to say what happened. We actually wasn't aware about this work before, but after all, this would be a computation about the hyperbolic surface, and which actually also applies for any hyperbolic surface. So let's do this. Let me just. So now if I want to compute this, all the Brownian loops in the homotopy class, homotopic to this geodesic gamma, I can look at this universal cover, like assume that my gamma would be lived to this geodesic going from 0 to infinity. Let's say this point here is here, and its deck transformation would take it to another point. So gamma is represented by this element with exponential length of gamma times z. And how a Brownian motion what kind of curves that would be homotopic to gamma? Okay, these are exactly the loops which start from one lift, x, to another point, which is of the form h minus 1 gamma h x. So this is in the conjugacy class of this gamma element, where this big gamma, this is the group, the Fuchsian group coming, the deck transformation on h. So okay, so this is really conjugacy. Why conjugacy class? Because say if h tells you one element in the fundamental group being going around one handle, so this will be going from one handle, going around gamma, and do the handle. So in the free homotopy class, this is homotopic to gamma. So now if I want to compute the Brownian loop measure, well, I just care about this mass, right? The mass, it will be integral some heap kernel. So remember, before the loop measure, I have to count all these Brownian loops that would be homotopic to gamma, or like the loops that would be lived to from one point x to this gamma prime of x element in the conjugacy class of gamma. And how much? So that was the wt x to gamma prime x. So its total mass, if I just want to compute the mass, it's a number. It's just given by this heat kernel. Okay, it's still averaging over time or the starting point. Now the starting point is chosen from the fundamental domain, but now I have to add up all the elements in the conjugacy class. But here, since gamma prime is of the form H inverse gamma H, the heat kernel should be invariant under isometries, so I can replace gamma prime by, I apply the map H for both elements, I will get H of x and gamma H of x. In other words, I can just integrate over a translate of f under H, and that will be the new element and the gamma of this new element. So that would turn this integral of f over a sum into a bigger fundamental domain, but without the sum. That was exactly the fundamental domain of this map. And this is a standard calculation for the hyperbolic surface. So summarizing, what we actually have shown is that the total mass of Brownian loop that's homotopic to gamma is exactly to the integral of the fundamental domain of this annulus obtained by modding out H by this element of gamma, which is this hyperbolic annulus. In short, it just say that each Brownian loop lives to the same, a unique curve here, and also the Brownian loop measure homotopic to gamma lived exactly to the Brownian loop measure in this annulus, and among all the loops that's homotopic to the central geodesic, the geodesic there. And since Brownian loop measure is a conformal invariant, it has to be a function of the modulus of the annulus, so it has to be a function of the length of the geodesic. And this length is the same length as this length. So from this, we see clearly that the total mass of Brownian loop homotopic to gamma is a function of the length of gamma. And that's really almost immediate. But then what exact function that is, so then we have to really do the computation. So I'm not giving out all the details, but it's actually really a standard computation for people who really knows computation for the hyperbolic surfaces. It's actually part of the proof of the Zellberg trace formula. But the only difference is that we also integrate by 1 over t. And we get this simple function, which is 1 over multiplicity times 1 over exponential length minus 1. And then you can also do the same thing for the torus. And this is much simpler. You can use the heat kernel for the Euclidean metric. Everything is really explicit, and you can do it in 3 lines. In the torus, you get area t divided by pi length squared. Notice that this is indeed the conformal invariant. If you scale the metric, the area will scale by squared, and here this is the length squared. Okay, finally, the proof of the mean result. We said that the Brownian loop measure is conformally invariant, but here we're not really making a conformal change. The metric is conformal outside of this cusps. And so you can't directly apply this. But on the other hand, the total mass of loops that goes through these points is 0. So what we can do is to take out some small epsilon neighborhood and look at the loops that doesn't touch this epsilon neighborhood. And then you see the loops outside of the epsilon neighborhood, they're conformally invariant. You can compute the total mass, they're the same, and then letting the epsilon goes to 0. And because the chance of Brownian loops touching those cusps is 0, in the end, when you let the epsilon go to 0, you cover every loop that would appear on the left. But if you want to compute the Brownian loop on the right-hand side, which are homotopic to gamma, well, now in this case, they will be separated into the sum of a union of homotopy classes. Each of them, they are computed with the same way, and you get the same expression, but now everything in terms of the hyperbolic metric on the right. And so then you almost immediately get this identity. After all, what we did is we compute the same Brownian loop measure in two ways, one on this surface, the other on this one. And we know a priori they're the same, but they give two different expressions. So if we take even one more step, the previous proof I showed you, it's just some integral of heat kernel, right? Why it gives you this? So the only thing we did is to give some interpretation of this heat kernel. When I take the integral of the heat kernel, I think that this is the total mass of some Brownian path, which closes up on itself. And the conformal invariance of the Brownian path, which by forgetting the starting point and the parameterization, it's really saying that now I can move my starting point to other points. So just giving one interpretation of this integral of heat kernel, you get more information and more tools from the knowledge from the Brownian motion. So I don't know if there's a proof without Brownian motion. There's supposed to be no probability in this story. Like even just the case of a torus and Wang's punctured torus, one can try to figure out if there's a direct way to show this. And I didn't find one, but also didn't try very hard. Yeah, so that's the end of the proof. Okay, so the second part of the story is very brief. It's about the total mass of Brownian loops, which has been already studied a lot by Yves and Julien Dubeda, et al. But we still want to try to do it slightly differently. Let me just tell you what this determinant of Laplacian is. Now we fixed the surface to be complete hyperbolic closed surface with finite genus. And it's hyperbolic. The metric's fixed. And the spectrum of the Laplacian is given, actually minus the Laplacian is starting from something 0 corresponding to constant function, and then all the positive term, and they grow linearly. And the zeta function is the same one as you define the Riemann zeta function, but where you replace 1, 2, 3, 4 by lambda 1, lambda 2, lambda 3, lambda 4. And this is well-defined. The sum is well-defined for a real part of S larger than 1, but you can do analytic continuation towards 0. And the log determinant of Laplacian is defined by minus zeta prime at 0. Heuristically, if you're allowed to take the derivative of this sum, you would get you do very formal computation, you get this log lambda I times lambda I to the minus s. Evaluate at s equal to 0, you get the sum, you get log of the product of lambda I. So of course you can't do this directly because they grow linearly, but in this way, introduced by Ray and Singer, say this zeta regularization at least give you a number which can be interpreted as the log determinant of Laplacian. And this is actually very much used in physics, and being this, every time you want to take a determinant of Laplacian, they use this. That is related to the Brownian loop measure. Heuristically, here I just rewrite this, the zeta function. I write this in a different way. So 1 over gamma s times this integral. This is just a change of variable. You could get immediately this identity. It looks a bit more complicated there. And when s goes to 0, gamma function has a simple pole at 0. So 1 over gamma s behaves like s. And then on the right-hand side, I just replace s by 0. You get t minus 1, trace of the heat kernel, exponential t Laplacian minus 1. And the trace of heat kernel can also be written as the integral of ptxx times the volume. Okay, this is in quote mark. You can't do this. This is infinite. But if I take the derivative in s and take its value equal to 0, well, the right-hand side, this doesn't have s in it. take derivative s, you just get this term, and I also ignore this minus 1. What I would get is this integral of t minus 1 ptxx volume. And that's exactly the mass of a Brownian loop measure would look like. That's a heuristics. And a concrete result, precise result, this actually happened also much earlier in the literature, but it's Morrison, Min Jae Park, Pfeffer, Sheffield, they formulated in terms of Brownian loop measure. They show that if you look at the Brownian loops, which quadratic variation, meaning the t parameter, less than, in between this t and big T, so you throw out small loops and throw out big loops, and you look at how they blow up. So with respect to the small loop, there is 1 over t blow up. About big loop, there will be log capital T blow up. But if you just remove this term, you remove this term, and there's a little t, there's also the log term, but these are like all constants. You can, the volume also, so everything is just constant, but then the remaining term here will be this log of zeta-regularized determinant. Yeah. So this really follows by like studying how this zeta function behaves, how you do analytic continuation, and how you separate the contribution from small loops and big loops. Oops. Okay, in our case, we want to do a bit differently. We don't want to do the small loop, big loop truncation, but we do this truncation by the homotopy class. I denote G of x, all the geodesics of x, P of x, all the primitive geodesics of x. The prime geodesic theorem says that the number of primitive geodesics of length maximal less than L, they have the expansion, which is depending, the first leading term is the Lie of exponential L, where Lie function I recalled it here. So it's asymptotically just exponential L over L. And there is a lower order terms, which depends on small eigenvalues of the Laplacian. And remember the Brownian loop measure we had, that was I recall that was 1 over, in the primitive case, it's just 1 over exponential L minus 1. Of course, I can't sum them up. There are too many of primitive geodesic. That's normal because we know that total mass has to be infinite. Okay. So our result says the following. Okay, if you just want to sum them up, I would just do the integral 1 over exponential L minus 1 d nxL. And this is the counting, and you sum them up. And we say, like, if you want to make it finite, you probably just want to remove this leading order term. This will be finite because the next term will be at most the exponential some number, which is this S of j will be a number strictly less than 1. And yeah, so then this difference will be integrable if you take this integral. And we get the following result. So minus log determinant of Laplacian will be minus area of x, which is just a function of genus, 2g minus 2, times E is a universal constant. We can compute it. And then next term is a constant term. And then you sum over all the geodesic, all the Brownian loops of homotopic of multiplicity larger or equal to 2. This term is always summable. And then the primitive one, which is normalized by this Lie function. And the key idea is it's just to also the Zelbert-Trace formula, which is we essentially proved it in this case for the expansion of the heat kernel. The heat kernel can be written contribution from trivial loops and the loops that are homotopically non-trivial. And if we want to get the log determinants, we have to look at this analytic continuation, and we separate the contribution of a primitive curve and non-primitive curves and some calculation, and that's it. Yeah. So finally, I want to ask one open question that I don't know the answer. Actually, the closed surface, that's actually harder because we need to do this renormalization. But if you start with a complete hyperbolic surface with at least one funnel and with finite genus, then the prime geodesic theorem would tell you that actually the counting of primitive geodesic is already is exponential delta L, where delta is related to the Hausdorff dimension of the limit set of the function group. So it's a number strictly less than 1. And you already get this sum of the Brownian loop measure of the homotopically non-trivial loops that are already finite. There's no normalization needed, but we don't know what this number should be. It should be some satisfying nice equations, can be viewed as a nice function on the moduli space, but we don't know. Yeah, finally, let me conclude. So in this talk, we saw that the computation of the mass of Brownian loops gives us that the total mass of Brownian loop homotopic to a given geodesic gamma is expressed as the length of the geodesic, which is this simple function. If it's primitive, it's just divided by m if it's non-primitive. And this allows us to study the length spectra of Riemann surfaces. And one application that I tell you is that we can relate the surface with additional punctures. And we also obtain some other renormalization of the total mass of Brownian loop and express as in terms of log determinants of Laplacian. And that's it. Thank you for your attention.